Good morning. Thank you. Thanks for being here to listen to me. I'm Ramesh Karuppusamy. Thanks to RS for introducing. So I'm a staff researcher from the Max Planck Institute of Radio Astronomy, and I work for the fundamental physics group there. And the institute is, by the way, in Bonn, Germany. Okay, so what I'm going to present today is work from others as well. For instance, especially Amit Bansod, who's been actually doing much of the firmware work, and then other scientists in the group. So what I'll talk about is pulsar processors that were enabled by CASPER technology. So some of these are being obsolete as we hear, so we're also trying to fight obsolescence and then see how to go forward. And yeah, so that's what I'm going to talk. So just to start with, this is the outline of my talk. I'll tell something about radio pulsars and then how we use pulsars as tools for fundamental physics. And then that is just to motivate why we do this stuff. And then finally, I'll carry on and tell you something about how the signals from pulsars look like. Guillermo already introduced, so I wasn't sure what he was going to say, so you'll see some repetition here. Sorry for that. And then I'll tell something about the pulsar instruments that we got, and then I'll finish with a summary. Oh, so this works. Yeah. Oh, super. So here we are again, just as Guillermo showed. So there's the neutron star. So what we have is radio pulsars. They are currently accepted that they are rotating neutron stars with extremely large magnetic fields. They are born when a massive star goes supernova, a star that's 3 to 10 solar masses, when it goes supernova, and then the star collapses into a neutron star because gravity is so strong that it crushes the atoms, and what is left over is neutrons. And because neutrons don't have charge, they can be compressed down to a very compact object, something like 20 kilometers in diameter. And the process of the stellar collapse misaligns the rotational and the magnetic axis, and that in turn gives this cosmic lighthouse effect. And since the neutron star is mostly made of neutrons and it's compact and it's very massive, but there are also ions in there, and those get accelerated along the magnetic field lines over here. And as the charged particles are accelerated along magnetic field lines, it emits radio emission, and that's what we see here on Earth. Since they are so compact and massive, they are very stable rotators, rivaling atomic clocks here on Earth. For instance, one of the best timed millisecond pulsar, just what Guillermo showed, it's the brightest millipulsar in the southern hemisphere. That's got a stability of 1 second in a million billion seconds, if that sounds fancy. So, and a good fraction of the millisecond pulsars are also found in binaries, which are also excellent cosmic laboratories, because you could do tests of gravity and stellar evolution and so on. To carry on, as I told you, they are very compact objects, so they are cosmic flywheels, extremely stable rotators. But because of the huge magnetic field, they slow down. When you rotate a huge magnet in vacuum, it slows down because of magnetic dipole radiation. So you could kind of write down as the spin down energy, that is the energy that it loses in its slowdown, is broken down into dipole radiation, and a good fraction of it is gamma rays, and a very tiny fraction is coming out as radio waves. So these radio energy is very tiny, but still it gives us a wealth of information. So just the two observed quantities, the pulse period and the way the star slows down, which is the p dot, tells what the surface magnetic field is and what the age of the star is. With these two quantities, you can build in one of these things called p dot diagram, where you have the period and period derivative, and that tells how a star is born, how it evolves. For instance, a young star is born here, a young neutron star is born here, spins fast, and then it slows down and moves into the normal population. And by chance, if it encounters another star, it gets spun up, and those are the recycled pulsars, which got low magnetic fields, but it spins very fast. So these are the millisecond pulsars that are quite interesting. So how do you use these objects as tools to do fundamental physics? These are very stable rotators, so the long-term monitoring of these objects are called pulsar timing, and that involves accurate measurements of the pulse period and the period derivative, the p dot. So with these, you could find out the masses of neutron stars if they are in binary, and that tells you something about. In some cases, you can find a star that is more than 2 solar masses, as in this case, 0438 plus 0432, which has got 2.01 solar masses, and that challenges quite a bit, challenges a lot of theories of the equations of state. There is the dense matter. You could also use these to test gravity theories, because when the two objects are in binary, you can see how they fall in the gravitational potential of each other, and that you can test alternative theories of gravity and rule them out as well. Similarly, pulsar timing array, which is monitoring an ensemble of pulsars that's distributed around the galaxy. You could try and detect the very slowly varying gravitational wave that's passing through the galaxy, and those are of the order of nanohertz, so which means you have to monitor at least 10 plus years to detect these very slowly varying waves, gravitational waves. You could also, because they are pulsed in nature, the signal that you get, the signal encodes information about the interstellar physics because of dispersion, rotation measure, Faraday rotation, and all of these are encoded in the signal. So all of that tells something about the interstellar physics and the galactic magnetic field, and also the magnetosphere of the pulsar, that is the immediate surrounding of the pulsar, has got very dense plasma, so you can also tell something about plasma physics. So I put in this slide to just show you the contrasting requirements that we have in pulsar science. So here we've got you can measure OH emission lines in the direction of the pulsar. In this case, you don't need much of the bandwidth. You need 1-2 megahertz of bandwidth, and that's it, except for very lots and lots of telescope time. On the other hand, you can to detect Faraday rotation, you need wider bandwidths. In this case, I'm showing a magneta that was discovered very close to the galactic center in 2013. So this was just 3 arc seconds away. And this magneta has the highest rotation measure that's known in the galaxy. It's got the rotation measure is about 67,000 radians per square meter. So, what's interesting about this is when we found this magneta, it was very clear that it's actually probing the vicinity of the supermassive black hole, because the black holes themselves, they do not have magnetic field. So much of this is kind of attributed to the environment around the black hole. And with 500 megahertz of bandwidth observed at 6 and 8 gigahertz, this is the Stokes QNU, and that rotates rapidly because of the magnetic field. You see that the error bars are quite large over here, as shown in this blue and red dots. But later on in 2017, when we had an instrument with wider bandwidth, with 4 gigahertz bandwidth, the ones that are indicated by the green dots over here, the error bars are much smaller. So greater bandwidth is, of course, a key to much of the science that we do. So yeah, the point again was to say that we need both narrow and wideband capability for pulsar work. At the same time, looking at the time domain, it's also extreme in some cases, because as I told you, you want to monitor pulsars for a very long time, so you're monitoring over tens of years. And then there are also phenomena that manifest in shorter than a nanosecond. In this case, I show a giant pulse from the crab that has a resolution of only 0.4 nanoseconds. So this is an extreme event. On the other hand, you see this Hulse-Taylor pulsar, a binary pulsar for which they received the Nobel Prize. So here, this was the first evidence of gravitational wave emission. In this case, the advance of periastron is changing over several years. So in this case, you're monitoring this pulsar over many, many, many years. And the plot here on the right also shows from an instrument in EFFELSBERG radio telescope by Shah et al. Published in 2012. This shows that the pulsar profile hasn't varied at all over all these years. And with this, they can kind of come up with a very stringent limit on the, the Lorentz invariance violation. So to move on, tell you something about pulsar signals. So we heard about pulsar dispersion. So here I show a signal with more extreme dispersion, a very simple pulsar. But we are observing from 600 up to 1.4 gigahertz, and this is how the dispersion curve looks like. So which means the signal arrive, the low frequencies arrive much, much later than the higher frequencies, and in this case, it's about 2 seconds. So if you are going to process this, definitely you need to buffer up this 2 seconds of data, Fourier transform, and remove this dispersion smearing. This dispersion smearing can be expressed as the dispersion measure, which is proportional to the total number of electrons in the line of sight. And this one, between two frequencies, if you see the delay, this is how it goes. So it goes inversely to the square of frequency. So which means at lower frequencies, the effect is worse. So you'd have to correct this. Only then you can time the pulsars accurately. So this is what we call dispersion. So you could do something called incoherent dispersion, where you just break down into channels. But each of these channels would still have dispersion in them. And if you don't correct for dispersion at all, if you just add the signal, then you get a blob with which you can do nothing. So you can do a little better. It's called incoherent dispersion, where you just remove the interchannel delays, and then you get a kind of fattish profile with which you could do something. But what is better is so-called the coherent dispersion. In this case, you model the interstellar medium as a filter that imparts this frequency-dependent delay. And then this is how it's modeled with a transfer function of this, and nu naught is the frequency of observation, and d is the dispersion measure. So if this is the impulse response, if you convolve your signal and remove this effect, then you can get a very sharp profile. And this is much, much better because it times extremely well. For instance, it's, as we see here in this profile over here, the blue curve is the fat profile is as a result of incoherent dispersion. And if you use coherent dispersion, the red curve, it doesn't render well, but you have to believe me, that's a very sharp notch here. And these things time extremely well, and you can get something like 60 nanosecond timing residuals in few hours. And that is key, because to detect gravitational wave signature, you want to time several pulsars in the 100 nanosecond or less in that regime. So this is how dispersion is removed in our case. So we get voltages from the polyphase filter bank. So in the computer, you run a large FFT and break down into channels. In these channels, each of these channels are multiplied with the dispersion kernel, and then you do the inverse FFT to do the convolution, complete the convolution operation. And each of these channels are then the data in each of these channels are folded with at the pulse period, and then you stack them up in time and frequency. So at this point, you could also compute your 4 Stokes parameters, or we normally compute coherence products, just the cross products, because you tend to observe with circular polarization feeds and linear feeds. So the coherence products are much more generic, which you can better calibrate later on. So if you've done everything correctly, so this is what you get, a pulsar that's nicely de-dispersed and also lining up in time very well. And this is what people then feed it into their timing code and then spit out the residuals, or TOAs, times of arrivals. So yeah, pulsars are interesting. So yeah, you can time them, but you have to discover them first. So So discovery is a new process because you don't know the period of the pulsar a priori, you don't know the dispersion measure. So at the minimum, you need to search in these two parameter space. So for this reason, you want to create a data that has both time and frequency resolution. So this is one of the projects that's currently underway at the EFFELSBERG Radio Telescope. So here, this shows the survey of the sky, an unbiased survey of the sky looking for pulsars. So you look for pulsars along the galactic plane and narrow region around the galactic plane, and then the intermediate region and the whole sky. So they are like along the plane. We want to look deeper. These are 1500 seconds pointing, and the data is dumped at 51.2 microseconds with 512 channels. And just to increase the survey speed, we have 7 beams on the sky, and they are tessellated in a way so as to get an optimal coverage. So this survey so far produced 30 pulsars, and then 4 of them are millisecond pulsars. The reason you want to look deeper in the plane is most of the interesting pulsars are in the plane, and that's the reason you're going to look deeper. Whereas you skim, as most of the sources settle along the plane, you don't expect to find much. And even if you find something over there, they might not be that very dispersed. So that is the reason you don't look very deeply above the plane. So now those are the signals. So that has to be converted to data. So what have we got? We got 2 instruments based on the Roche 1 and Roche 2. So we have an instrument that is that's called PSRX. That's operating in EFFELSBERG, but it's also being used in these 2 telescopes. The instrument based on Roche 2 is mainly meant for high-frequency observations, and they are used in EFFELSBERG for observations beyond 4 gigahertz or above 4 gigahertz. And they find their way also at the IRAM 30-meter and the ABS 40-meter telescopes. So what do we have with the PSRX or the Roche 1 instrument? We got 512 megahertz mode for timing and as a baseband backend. It can produce polyphase filter banks with 16 or 32 channels, like with 25 or 16 megahertz subbands, or you can have a non-PFB version which dumps the data in at 320 megahertz or 500 megahertz with one nanosecond resolution. So this is so-called coherent firmware with which you can coherently de-disperse and get good pulsar timing. So the whole stuff is done in real time. The data from here goes into a small 16-node cluster, CPU cluster, where it's coherently de-dispersed. We have a GPU node that does that can process this data. The PSRX2, it's got a bandwidth of 4 gigahertz. You can time. You can use it as a coherent backend with a bandwidth of 4 gigahertz, or you can use that as an 8 gigahertz search mode backend. So in terms of search mode backend, it has a variety of firmwares that does 2K, 1K, or 512 channels, full Stokes, down to 16 microsecond dump times. The device can also be reconfigured because you have the Asia A ADC, which could be used in dual mode, and then you can have many more inputs, and then this can you can sample down to 64 microseconds, and this is the coherent mode. So these are the telescopes, the 100-meter radio telescopes, the Level 76 meter, Sardinia 64 meter, and the Yabis 40 meter, and the IRAM 30 meter telescopes. So this is how the instrument setup in EFFELSBERG looks like, a variety of instruments generating a variety of bandwidths. So these are the Roche 1 systems, these are the Roche 2 systems, and this is the bit that I was talking about, where you could configure the Roche 2s in dual input mode, the 5G ADCs, if I do not mention. So so you can run these in parallel and then produce process all 7 beams. This has turned out to be a very bad idea because of very complex way in which you have to switch these signals in here. So all of the data ends up in these switches, which get distributed to the computers where you can process them. And we've got a high performance distributed file system that can do 32 gigabits per second to disk. So also important that we use PSR data, a modified version, and DSPSR to really pulsar coherent de-dispersion, and Mellanox VMA that scales up to 32 gigabits per second sustained data throughput to the disk. This is how the instrument looks like, the Roche ones with the IADC and a Velen synthesizer. And this is the Roche 2 instruments with two 5G ADCs, again a Velen synthesizer and a Raspberry Pi for controlling these switches, which are tucked in right over here. And yeah, a messy rack with all these stuff in there, a 40 gigabit and a 10 gigabit switch and the computers that go with it. So this is how the firmware looks like, the Roche 1 firmware, which is a packetized astronomy signal processor originally from Berkeley by Terry Philiber, if I remember right. So yeah, the PFP stage, and then what we've done differently is we've put in the 1 PPS from the MESA, and that generates a marker that is inserted into a data stream. So initially the firmware had some issues, which we found this was a satisfactory way to solve the synchronization problem. And then the marker data byte is detected in the processing stream, and then that is used as an absolute timestamp. And then we've got, since I'm running out of time, I'm going to cut this short. So this is the Roche 2 firmware, where the only difference over here is we compute Stokes, and you can accumulate, and then you can bring it down to 8 bits before you can transmit to the receiving computers. So far so good. So except that we have issues with the Roche 1, very ancient hardware with CX4 and parts that you can hardly get. And the impending end of life that is being announced for the Roche 2. And therefore, yeah, in the interest of continuing timing, for Pulsar timing, I'm thinking about replacing this hardware. So the basic thing is that we need to have a compatible timing mode. This has to run for 10 or 20 years time scale. Then we need to at least, any new solution needs to run in parallel for at least 1 or 2 years, so that you understand the systematics of the new instrument, because you need to monitor these pulsars very, very precisely. And then there should be a possibility of adding newer modes, because as requirement arises, for instance, FRB triggers or RFI, we need a tool flow with which you could also add modes to the instrument. So therefore, thinking about the RF SOCs, and then in the long term, things would be digitized up in the focus and then distributed into a generic processing fabric, but that's really the very long term. And so finally, here's the summary. I'll leave you with the summary slide, and I want to use this opportunity to thank the CASPER community, and also to Willem van Straat and Andrew Jameson for DSPSR and PSR data. That was it.